In September 2025, a study published at the Proceedings of the National Academy of Sciences claimed that the prevalence of disease like obesity and stroke were increased by the policy of the changing of the clocks, daylight saving time. Now, a response letter published in April 2026 shows that this came from a mathematical illusion rather than from evidence. This video talk will show why. My name is José María Martín-Olalla. I am professor at the University of Seville in Spain, and with Jorge Mira, professor at the University of Santiago de Compostela, also in Spain, co-authored this response letter. So let's go with the presentation of the storyline. What is this about? In September 2025, two persons at the Stanford University, Lara Weed and Jamie Zeitzer, sorry about their pronunciation, published a study that linked obesity and stroke outcomes with different permanent US time policies. In November 2025, we submitted a letter reply, which has been published in April 2026. Concurrently, a professor from a University of Germany, Thomas Erren et al., submitted another letter reply that also got published in April 2026. And in their letter, they challenged the study from an epidemiological point of view. Also in April 2026, concurrently to the letter replies, Lara Weed and Jamie Zeitzer also published a reply to our previous letters. So, what is the original study? The original study is aimed to analyze the impact of clock policy in the long term. I mean, usually studies aimed to understand the impact of the time policy focus on a week or a fortnight after the transition has occurred. And we know the existence of slight effects associated with the very moment at which the transition occurs. This study is different in the sense that they try to predict or to understand how the policy impacts globally year after year and during a year. And this is a very complicated thing to do, because unlike with the short-term studies, we don't have a natural experiment to perform this kind of studies. And these kinds of studies are also jeopardized by the fact that the season exists. And in fact, the current clock policy is aligned to seasons. So anyway, they try to make this kind of global outcome of the current policy. And the study just got to the news. I mean, it was very well propagated into the news. There are some 200 news outlets making a history of this linking. It is important, of course, or it looks important. It is the third most cited study in social media from PNAS with a similar age. So it is a blockbuster from the point of view of mass media. Here is the methodology of the study. The authors propose a light diet, which is a specific way in which the individual is exposed to light. There are two light diets, one for the weekdays and determined by work, and the second one for the weekends and mostly undetermined by work. Of course, it is just a free time. So it is associated with the sun, it is associated with seasons, it is also associated with standard conditions in work environments. So these light diets are feed a circadian model. A circadian model is a set of differential equations, and the thing is to convert these light diets together with the chronotype of the person into some outputs, which is informing about the circadian phase of the individual. So the authors considered 3 chronotypes: early chronotype, intermediate chronotype, and late chronotype, that differ more or less in 0.2 hours, which is 12 minutes. So this is just a number to distinguish between different chronotypes. Now, after those differential equations are solved, the output is the circadian phase, and exactly the output is the core body temperature, which is CBT in this study. I mean, the temperature of the body of the individual. And the phase is determined by the time of the day at which this core body temperature attains its minimum value. It is the circadian law. It is the moment when the basal activity is the lowest and the core body temperature is also the lowest. So this is the phase, the circadian phase, just an arbitrary moment in our daily life. The daily period is the time elapses between 2 consecutive CBT minimum. Okay? So this is one day from the point of view of our circadian clock, our physiology. And the shifting time, or the daily shifting time, is the difference between this daily period and Earth's rotation period, which is 24 hours. So this shifting time, this daily shifting time, is the regulatory circadian shifting necessary to stay synchronized with the outer world, with the Earth's rotation. So it is kind of a regulatory mechanism that keep us fixed, keep us synchronized with the environment. And this daily shifting time is accumulated to give the yearly accumulated daily shifting time, which is the total shifting of the individual in 1 year. We must also take into account that the time step of this model is 5 minutes, meaning it is below the difference between chronotype. And this is also important in the sense that when we are speaking of the time elapsed, the daily period of the shifting time, this daily period, this shifting time, is impacted by the fact that our time resolution is 5 minutes. So for instance, a daily period can be 0 or 5 or 10. It can't be 2.5 minutes, for instance. So the results of this model is this total circadian shifting times in the United States for the 3 time policies and for the 3 chronotypes. So it is a set of 9 heat maps that are here shown, and we have a value around more or less 20 hours per year of total circadian shifting. Is it high? Is it low? Well, let's see. Here is the association with obesity. I mean, this is the change in obesity prevalence that the author predict from these yearly circadian shifting times. So it is a small shift. It is only 1% below low. It is 1% down. But it is significant in the sense that the prevalence of obesity is, of course, a matter of concern in modern daily life. Let's go with the guts of the analysis. Here you can see the core body temperature minimum as obtained from the code that the authors provided in their submission. Here in blue is the core body temperature for standard time, winter time, for summer time, daylight saving time, and for seasonal clocks. This axis displays the hour of the day always in standard time format. This curvy line is the sunrise. Okay, so here in this setting for the standard time, we have a phase, a core body temperature minimum at the core body temperature around 4:45 a.m. Well, in the sleep phase, if we think of the winter and the autumn, in summer it is around sunrise time. Here it is 1 hour earlier, of course, because of the shifting of the clocks, if we are using daylight saving time. And here we have the bimodal phase, where the phase is different in winter and in summer. And this is, of course, associated with the fact that the sunrise time is varying across the season. This is happening for some 35, 40 degrees latitude. This is not happening at the equator, for instance, and it is much stronger at polar latitudes. So if you can see, if we focus our attention on the phase, on the blue lines, we see that this is a pretty stable signal with some noise. I mean, the noise comes from the fact that the model can only, I mean, this is one tick for the model. This is delta with 5 minutes, one tick in the model. So the model can only set the core body temperature minimum here or there. Say here or there, here or there. There is no in-between number for this metric. The circadian shifting, the shifting time, is the difference between two neighboring minimums. And this means that we are just making the derivative of this signal or this signal or this signal. By the way, I forgot to mention, this is pretty stable unless we are on transition dates, of course. On transition dates we have a quick changing from the phase of the one clock to the phase of the following clock, either in spring as in autumn. Okay, so when we take the shifting time, I mean the derivative of this signal, we of course obtain something which is distributed around 0. In fact, if we add up all these shifting times, we had 0, 0, 0, or eventually, this is for San Francisco, eventually in some other location in the United States, we may have some very, very small number, because we are adding positive signals, positive values, and subtracting the negative of values, and we are just readjusting our phase to fit with the environment. So the question is, how does this 20 hours total shifting time arise from? I mean, how is this number built? And the thing is, we inspected the code provided by the authors, by Lara Witt, in fact. We inspected this script, which is a MATLAB script, and we found that the authors were summing, were adding, were accumulating absolute values of the shifting times. And indeed, the study lacked a narrative on why they were utilizing these absolute values. It is only referenced here. I mean, across the year, we computed cumulative absolute shifting times under each time policy. We are not chronobiologists, we are not physiologists, we are not in the loop with this kind of metric. I mean, it is strange that we use this kind of absolute shifting, absolute differences to perform this kind of metric. We will come to that later. So when you do this absolute shifting times, when you do this absolute derivative, you are now accumulating values, and then the sum builds up to 20 hours per year, more or less. Is that number large? Well, it is not, in fact, because nonetheless we are just speaking of small shifts, perhaps with some few exceptions, but it is very narrow in time. On average, we have some like 3 minutes per day of absolute shifting time, which makes only 0.2, 0.3% of a day 0.2, 0.3% of a year, 0.2, 0.3% of whatever unit of time you may want to look. So the predictor for this kind of analysis is just 0.2, 0.3% of the signal. And the question is how this weak metric can explain or can be linked or can be associated with the prevalence of disease like obesity, like strokes, like diabetes, and so on. And this is the real question that puzzles us and puzzles the German professor that also filled a letter. In their reply, Weed and Seitzer said, "We intentionally selected a simple and physiologically grounded metric. However, absolute value is not a simple function. It is not invertible. It can't be undone. And we lost track of the phase when performing this absolute value. And for this reason, it may not be physiologically grounded because we can build up non-regulatory phases that lead to the exact same absolute shifting time." And we are going to see that here now in this section. So this is the signet, the real shifting time, which is nothing but the derivative of the phase. And if we take the derivative of the phase and obtain the shifting times, we can undo the operation by integrating the shifting times to retrieve the original phase. And this is just fairly simple. When we perform the absolute derivative, there is the point that we lost track of the sign of this difference, and therefore we lost track of the phase itself. We cannot undo this operation. We can add positive absolute shifting times, or we can add negative absolute shifting times, or we can add or subtract absolute shifting time depending on our choice or depending on a random choice. But these three phases, neither of these three phases are the original phase. The original phase are only retrieved if you retain the sign of this absolute derivative, the original sign of this difference. And this is not possible when you perform the absolute derivative, the absolute value of the difference between two consecutive phases. And the problem with that is that these phases can be non-regulatory, meaning that this can delay day after day, or they can advance day after day, while having the exact same daily absolute shifting time, and therefore the exact same total absolute shifting time. We can see that in action here in this simulation, in this visualization. Here we have the original data by the original study, and here we have this rebuilding with the absolute shifting values being added to the initial phase. So here we have a 24-hour analog clock. We have here the initial phase. It is around a bit before 5 p.m. and here we are now running the visualization. We will be shifting the day. This is for January the 1st, and we will move in throughout the year. And while moving throughout a year, the phase will be moving, and the day, the sunrise and the sunset will be also shifting. So let's go. You can see how on the left the phase is stable, while on the right the phase is accumulating, is adding and adding values, and at the same, always the absolute total shift is the same on these two signals. But here we have already the phase is still fixed on a little before 5 a.m. Well, here the phase is already 7:15, and it is around February, or February not, this is around May. And so, I mean, quickly we will have the transition date. We are now in the ST mode in the original data, and here this phase is the minimum of the core body temperature is around 9 a.m. I mean, well in the day, and of course, coming throughout the year, this is just it's making things worse and worse and worse. And the point is that this behavior is retaining always the same absolute total circadian shift. And the point is how this metric can predict anything related to health issues if it is undetermined. I mean, several different phases with very different behavior can lead to the same predictor for these health issues. We are now almost completing the year. Here it is, we have here, and now the year is completed. And this is our 20-hour total shifting, absolute shifting time, which is set in both signals. But this signal is non-regulatory. I mean, it's moved across the day, from day to night, from dawn to dusk, wildly. So, in conclusion, the methodology of this study is wrong. It looks intended so that the current policy gets the worst scores. So it is kind of a study which is sick of confirmation bias. The conclusion of the original study relating the clock policy with a disease like obesity or stroke are meaningless because, in fact, we cannot differentiate what happens with either policy under this methodology. This is all there is to it. I hope you have enjoyed this video. Have a nice day.